Have you ever stopped to think about what really happens during a collision? Or what it takes to get something moving? Well, we're about to uncover a hidden rule of motion, a physical law that's at play all around us all the time, from a tiny nudge to a massive impact. Let's get into it.
So, let me ask you this. What could a huge, speeding truck possibly have in common with a lightning-fast karate chop? I know, it sounds a little bit like a riddle, right? They seem like they're from completely different worlds, but believe it or not, they are connected by one single, incredibly powerful idea in physics. And the answer is pretty amazing.
We see clues to this connection everywhere. Think about it. A little table tennis ball just bounces off you, no big deal. But a hard cricket ball coming at you at high speed, that's seriously dangerous. Or look at a truck. When it's parked, it's just a big hunk of metal. But that exact same truck, even moving at a slow walking pace, has a massive, potentially destructive impact. So it's pretty clear it's not just about how big something is, or even just how fast it is. It's about both.
And this special property, this combination of an object's mass and its speed, actually has a name. A guy you might have heard of, Isaac Newton, called it momentum. This idea, momentum, is the very first piece of our puzzle.
So, what is momentum, really? It's actually super straightforward. You just take an object's mass and multiply it by its velocity. That's it. We call it P in physics. So, P equals m times v. The key thing to remember is that anything that's moving has momentum. And if something is standing perfectly still, well, its velocity is zero, so its momentum is zero too. You can think of it as the amount of motion an object has packed inside it. So then, what does it take to get a lot of momentum? Well, you've got a couple of options. You could have a really, really massive object, like that truck we talked about, or you could have something with a crazy high velocity, like that cricket ball. And of course, if you have something that's both heavy and fast, like a bullet train, then you're talking about an absolutely huge amount of momentum. Okay, so we've got a handle on momentum. It's mass in motion. But that's not quite the whole picture. There's another piece we're missing. A really crucial ingredient that connects momentum to something we experience every day, force.
Imagine this. Your car's battery is dead and you need to push it. If you give it one quick, hard shove, what happens? Pretty much nothing, right? The car barely even budges. But what if you lean in and apply that same amount of force, but you do it continuously, over a few seconds? The car starts to roll, it picks up a little speed, its momentum changes. This tells us something vital. Changing momentum isn't just about how hard you push, but for how long you push.
And that brings us to the absolute heart of the matter. The big idea is this. Force is the rate at which momentum changes. You see, the faster you try to change something's momentum, either starting it, stopping it, or changing its direction, the more force is involved. This simple, elegant concept is the core of what we call Newton's second law of motion.
And here it is in all its glory. This is the official definition. It sounds a bit dense and academic, I know, but all it's really saying is that the force you apply is directly tied to how quickly you change an object's momentum. Now, let's break this down and turn it into one of the most famous equations in all of science. All right, let's unpack that. The change in momentum is just the final momentum, that's mass times final velocity, or mv, minus the initial momentum, mass times initial velocity, u. Easy enough. Then, rate of change just means we divide that whole thing by the time it took for the change to happen. We'll call that t.
And since Newton's law says the force, we'll call that F, is proportional to this whole expression, we can write it out just like this. We are so close now. The force is proportional to the mass times the change in velocity, all divided by time.
Now take a look at that little bit in the parentheses, v minus u divided by t. Does that look familiar? The change in velocity divided by time, that is the literal definition of acceleration. So we can just replace that whole chunk with the letter a for acceleration. And suddenly, this big, complicated thing simplifies down to this. Force is proportional to mass times acceleration. And it gets even better. Because of the way we defined our units of force, like the Newton, that proportional to symbol becomes an equal sign. And there you have it, F equals ma, one of the most important equations ever discovered. It's so simple, yet it gives us this incredibly powerful way to calculate and understand the forces that shape our world. Okay, so it's a cool equation, but what's it good for? Well, it turns out understanding this law isn't just for physicists.
It allows us to engineer our world in ways that can be incredibly clever and can even keep us safe.
So let's circle all the way back to the beginning. That cricket ball is flying through the air. It has a ton of momentum. A fielder needs to bring that momentum all the way down to zero. How on earth do they do that without shattering every bone in their hand? Well, they use Newton's law, whether they know it or not.
Have you ever watched a pro catch a ball? They don't just hold their hands still. As the ball hits, they pull their hands back with it. What they're doing is genius. They are increasing the time, that's t in our equation, that it takes for the ball to stop. And by making t bigger, they make the overall rate of change of momentum much smaller. A smaller rate of change means a smaller force. The impact on their hands is gentler. It's beautiful physics in action.
And here's another place you see the exact same principle. A high jumper flies over the bar and then comes falling back to earth. They've got a lot of downward momentum. How do you stop them without causing injury?
You use a big, soft, cushioned mat. That mat does the exact same thing as the fielder's hands. It squishes down, which increases the amount of time it takes to bring the athlete's momentum to zero. A longer time means a lower rate of momentum change, and that means a much smaller and safer impact force on their body. It's the same trick all over again. But now, for our last puzzle. Let's go back to that karate chop. A karate expert isn't trying to reduce force, they're trying to create an absolutely massive one. How do they use this law to do the complete opposite of the fielder and the high jumper? Well, this is the other side of the coin. The expert's hand is moving incredibly fast, so it has a lot of momentum. They bring all of that momentum to a dead stop against the ice in a fraction of a second. This makes the time t unbelievably small. And what happens when you divide by a tiny number? You get a huge result. The rate of change of momentum is enormous, which creates a gigantic force, a force big enough to shatter a solid block of ice. So, if there's one thing you walk away with, let it be this. It's all about time. Whether you want to make an impact soft and gentle or incredibly powerful, the secret is controlling the time over which momentum changes. Increase the time to reduce the force, decrease the time to maximize it. It's a hidden rule that governs so much of what we see and do.
Once you know this relationship, you start seeing it everywhere. In the crumple zones of a car, in the design of airbags, even in how a boxer rolls with a punch. The physics is all around us. So now I'll leave you with a question. Where are you going to spot this hidden law at work next? Thanks for joining me.